Hello again everyone, welcome back to ptet.chemistry channel. So in this tutorial video, I'll go through this work 6 which is associated with the part in the lecture tutorials or the lesson notes on limiting reactant and excess reactant as well as percentage by mass. Alright, so not in that particular order but a mix and match of those particular concepts. So here we have two equations. So this is molybdenum steel. Molybdenum is this chemical, this element, Mo, the symbol. It's somewhere in the middle of the periodic table. If you see chromium, Cr, just below Cr, then you get molybdenum. And then it's reacted with aluminium to give you back the molybdenum metal and aluminium oxide. So Al3 plus and O2 minus. This is called iron 2 oxide, iron 3 oxide. Because what you have is iron 3 plus and O2 minus, and then reacting with aluminium will give you the iron as the metal, as the element, and aluminium oxide again Al3 plus O2 minus, which I hope you can see that that's how they combined because of the nature of how you would draw the dot and cross, as well as how you would combine the cation and anion to give you a formula unit. Alright, so this molybdenum steel contains 20% by mass, all right, not by mole but by mass, and you want to get 1000 gram of molybdenum steel. So you want 1000 gram of these, but you don't know how much mass of these do you want. And you know the molybdenum steel contains 20% by mass of molybdenum. Hang on, you want 1000 gram molybdenum steel, not molybdenum, careful, not pure molybdenum. Molybdenum steel is a mixture of these and these. Alright, so molybdenum steel is not pure molybdenum, which is element. So there's one thing you need to interpret the question carefully. It says molybdenum steel is a mixture. Alright, so it's not pure molybdenum. So 1000 gram is not for this. Be very careful. Alright, because in that 1000 gram only 20% is molybdenum, because molybdenum steel contains only 20% by mass of molybdenum. So I guess the first thing I will need to do, actually they want your answer to 3 significant figures, so don't forget that as well. The first thing I would do is probably out of 1000 gram of the molybdenum steel, which is the mixture, not the element, then what is the mass of molybdenum? Alright, because the mass of molybdenum is the pure molybdenum. Out of the steel, how much of it is actually molybdenum? So 20.0% means 20 out of 100, there's percentage, multiplied by 1000 gram. So put that into your calculator. 20 divided by 100 times 1000, that give me 200 gram. So I now know I want 200 gram of molybdenum, but I don't know how much mass of this do I need. Hope you can see that, you know, the mole ratio there, should probably use a different color, is 1:1. Mole ratio is not mass ratio. This is mass, these are mole. So what I need to do now is the mole of MoO3 is to the mole of Mo is 1/1 is equal to, now I need the Mr or MoO3, I also need the Ar or Mo. The Ar or Mo is already given here, which is 96. So the Mr of MoO3 is 96 times 1, because there's only one molybdenum, plus 16 times 3, because I've got 3 oxygen, each of which is 16 relative atomic mass. So 96 plus 16 times 3, I get 144. So in my typical setup for mole equation, this is the mole of MoO3. I need the mass of MoO3, so you know the mass of MoO3 divided by the Mr, which is 144, which I did on the far left hand side. And then on the other side, I know I have 200 gram of molybdenum in that 1000 gram of steel. These are in gram. So mass in gram divided by the relative atomic mass of the molybdenum divided by 96. Since it's 1 and 1, I can just bring up my equation. So if you can see, I can just bring this up. So 200 over 96 times 144 is equal to the mass of the MoO3. So I first bring this one up, and then I bring out another 144. I've kind of skipped one step there, but if you can't see it, do it step by step until you actually can see what I did there. But that was what we have been doing for all our mole calculations so far. Alright, so there's 300 grams, so there's 300, the unit of which has been given there. And they want your answer to 3 significant figure. This so happened to be 1, 2, and 3 significant figure already. So you know, it's just coincidence like that. This is 1, 2, and 3 significant figure. So this is already nice and straightforward there. On to the next question, we have this strange looking name, Rhodochrosite. So it's a carbonate ore of manganese. Manganese has this chemical symbol, Mn. It's just in the first row of the transition metal, the transition element, which is in the middle of the periodic table, that block. And you look at the first row, it's got this symbol, Mn. It does not contain hydroxide. Hydroxide is OH minus. Now what do we have? We are reacting 2 grams of rhodochrosite and we produce 148 cm3 of carbon dioxide. So I have the volume of carbon dioxide. These are room conditions, so that means the carbon dioxide is a gas. This is not volume of solution, this is volume of a gas. They don't tell you that, but you're expected to know that CO2 is a gas at room temperature and pressure. So I can get the mole of CO2 by relating this to molar volume, which is given in your periodic table for free at the bottom of it. Molar volume is the 24 dm cube or 24,000 cm cube that 1 mole of any gas occupied. This is given in cm cube, so I would have to use molar volume of gas, which is 24,000 cm cube per mole, where 1 mole of any gas occupies this much volume, 24,000 cm cube or 24 dm cube. I have the mass of the rhodochrosite, and that rhodochrosite is a carbonate ore of manganese, which is that. And I have excess HCl, so I'm not going to use that for any of my calculation. What is the percentage of MnCO3 in the rhodochrosite? It's an ore, so it's not 100% MnCO3. This is 100% MnCO3 based on this equation. Carbonate plus acid give you salt, water, as well as carbon dioxide as one of your 5 general word equations, which you have covered many lecture tutorials ago, and which I keep on telling you, if you know your word equation, you can do a lot of chemistry. From that equation, so what we have is, out of the 2 gram, not all the 2 gram is this, but we know the amount of CO2 that comes from the carbonate. If I have these, I don't know these, I can find out the mass of these if and only if I work out the MR of the MnCO3 first. So they've given you the AR here, which is more accurate. They are more accurate than the one given in your periodic table. So you should probably just use these, but bear in mind that in the O level, your periodic table just give you 2 whole numbers, so you can just use those if it is not given like this in the question. So since it's given the question, so it's 54.9 times 1 plus 12.0 times 1 plus 16.0 times 3. So that gave me 114.9. Alright, so it's actually gram per mole, which is the MR. Anyway, so what I'll do now is I'll link MnCO3 and CO2. So hopefully you can see the mole of MnCO3. Actually, I was going to do CO2 on top, but it really does not matter because it's just mole ratio. 1 mole of MnCO3, because 1 is in front. 1 is in front of CO2, that's why you don't show it. That's why it's 1 CO2. From the balance equation, and then equal to the actual mole. Alright, the actual mole of MnCO3 that reacted is the mass. You want the mass of MnCO3 that reacted divided by the MR. Mass over MR will give you mole of the MnCO3. At the bottom I have a gas, so this is volume of a gas in cm cube, so I'm going to use my molar volume in cm cube per mole. Then I express that going up because I want to make the mass of MnCO3 as my subject. So what happened is the mass of MnCO3 is equal to 148 over 24,000 multiplied by 114.9. What I will not do is I will not write down equal because it's no longer equal. The equal is now here. It's just saying that the next step is this. So do not use equal randomly because they have different meaning. 148 divided by 24,000 multiplied by 114.9. That gave me 0.70855 gram. So that means if I get this much carbon dioxide, it comes only from 0.70855 gram of these, of which I actually had 2.00 gram of the ore. So how much of the 2 gram is actually MnCO3? So the percentage of MnCO3 is going to be how much of it is MnCO3? 0.70855 divided by the total mass, which was 2.00 gram. So out of the total, how much of it is actually MnCO3 that will react with the acid? So the gram and the gram cancel. That is why you're calculating percentage. So your previous answer divided by 2.00 times 100%. I've got this exact answer, which is 35.4275%. However, they want your final answer to 3 significant figure. So this is 1, 2, and 3. So I'll look at the 2. This is lesser than 5. So this will be rounded up to 35.4%. This is 3 significant figure. Pretty stingy of this question to give you 3 marks, but you know, it is whatever it is. Should be able to work this out. Should be able to, you know, at least set out the mole ratio and find out what is the mass of MnCO3. Should be able to understand that out of the 2 gram, only this much is MnCO3. So you're working out the percentage out of these 2 gram. What is the percentage of MnCO3 in there? In the next question, so we are given this equation. So this is titanium chloride with magnesium given as magnesium chloride and the titanium metal. But importantly, they are telling us it's got 90% percentage yield. So we have 1000 gram of titanium Cl4. They've given us the relative atomic mass of that. And of course, you can work out the relative atomic mass of these from the periodic table, since you're expected to know the first 20 elements anyway. So given in the periodic table is 35.5. So the relative molecular mass of titanium tetrachloride, tetra because there are 4, so Mr or TiCl4, label your work, okay? You do not want to be someone who cannot label. So there are 4 of that 35.5. This is how you work out Mr, the sum of the individual relative atomic mass. You have 1 titanium and you have 4 chlorine. That's the meaning of that formula, which you would have done many weeks ago, provided you do actually understand what you have learned. Now 90% percentage yield, what does this mean? Usually a balanced equation means all of the reactant goes to form the products. So the percentage yield will be 100% because all the reactants reacted. So now you get the titanium from the titanium Cl4, 1 mole of titanium Cl4. So I'm writing this down, but you don't really have to write it down. This is the idea. 1 mole of TiCl4 should give 1 mole of titanium if 100% yield. But 90% yield means 1 mole of these only give you 90% of what you expect. So 90% yield means 1 mole of TiCl4 only forms or only gives 90%, which is 90 over 100 times 1 mole of titanium. Because 1 mole should give you 1 mole, but 90% means 1 mole only give you 90% of 1. Alright? So that's where I can set up my mole, mole ratio. The mole of titanium over the mole of TiCl4. What I actually get from 1 mole of TiCl4 should give me 1 according to the balance equation, should be 1. But in reality, they are telling us 90% percentage yield. So I don't get 1, I get 90 over 100 times 1. That is what happened in reality. That's what I actually get. So what is the mass of the titanium? This is how many mole of titanium actually obtained, assuming 90% conversion, but from 1 mole of TiCl4. Now this is the actual number that you get. You use up 1000 gram of TiCl4. So this is in gram, so mass over mR. TiCl4 is at the bottom, so it's 1000 over 190, which I work out in my first step. Mass over mR, mass in gram divided by mR in gram per mole. This is the actual mole of TiCl4. On top, they want the mass of titanium. So the mass of titanium as an element, I'm going to divide it by the relative atomic mass of the element. Mass over Ar is going to be mole of the titanium. Alright, so the difficult thing is this bit, because you're assuming usually always from the balancing question, but the question specifically tell you that not all 1 mole goes to 1 mole. Instead, 1 mole give you 90% of however much that number there is. Now I just need to work out the mass of titanium. So doing your rearranging of your mathematics, so 90 over 100 times 1 times 1000 over 190, because I'm just bringing the whole of that up there. Divided by 1 is just itself, and then I still have 48, which I can bring up there, so it's multiplied by 48. If you're not comfortable doing this in one step, write it out in 2 or 3 steps, but over time you've got to be able to do this much quicker, otherwise you will have problem well, completing any exam paper at all. All right, so you want your final answer to 2 significant figure, because you did read the instruction, 2 significant figure. So that will be 1 significant figure, 2 significant figure, so that is greater than 5, so that will give me 230, and they will be in gram, because I've expressed this one was in gram, this is also in gram, because gram over gram per mole, gram over gram per mole, they will give you mole over mole, which give you, mole over mole. And the answer will be 230 gram, just like that. Question 4, so this is reading from the table. So we're given 3 different formulas that contain iron. They are ores of iron. Which ore shows the greatest percentage by mass? And explain your answer. So we got to work out each and every one, the MR first of all. Because out of the MR, how much of it is the iron? Okay. So from your periodic table, iron is got relative atomic mass of 56. So 56 times 2 plus 16 times 3. This should be a quick enough exercise for you. And the percentage of iron in there are 2 iron out of this 160. There are 2 iron, which is each of which is 56 divided by 160 times 100%. So 56 times 2, I get 112 divided by 160 times 100%, I get 70% of iron. In the second one, so I work out the MR of Fe3O4. So these are very quick exercise, and they should come more naturally to you, assuming that you want to do well in this very simple and basic exercise. Percentage of iron, you have 3 iron. Doesn't matter 56 times 3 or 3 times 56, they're going to give you the same thing anyway on your calculator. 56 times 3 divided by 232 times 100%, I get 72.4% to 3 significant figure. Not that it matters that much at this point, so 72 or 72.4%. And last but not least, if I do it for the siderite, which is the iron 2 carbonate, so the MR of FeCO3, because it's Fe2 plus CO3 2 minus, so that is 56 plus 12 times 1 plus 16 times 3. There's 1 iron, there's 1 carbon, there's 3 oxygen, so they give me 116. So the percentage of iron, of which there's only 1, so it's 56 times 1 out of the 116, and then multiply by 100%. That would tell us the percentage of iron, the percentage composition of iron by mass. So that is 48.3%. So out of all these 3, I hope you can see the greatest percentage by mass is going to be the 72.4. So therefore, 72.4 is the Fe3O4, which is magnetite. And when they ask for explanation, I have just explained it in terms of showing the working. all right, showing the working to work out the MR and then the percentage of iron. That is my explanation, and I got the answer just like that for that last 2 marks there. Now this table shows the concentration of different ions found in a sample of aqueous industrial waste. These are concentration in mole per dm cube. How much mole of the ions in 1 dm cube of the water or the solution. Use the information in the table. Now you want the mass of dissolved iron 2 plus in 25 dm cube. Read very carefully. You want iron 2 plus. If you read carefully, the table gives you all the information you need. This is 0.450 mole per dm cube. Now they want it in gram in dm cube. So first of all, what I would do is, what is the mass? The mass in 25 dm cube. Actually, I'll work out the mole first. What is the mole in 25 dm cube? So the mole, actually, I'm not going to do that. I should really label my stuff properly. The mole labeled as n bracket Fe2 plus in 25 dm cube is going to be 25 dm cube multiplied by 0.450 mole over dm cube, because the dm cube and dm cube will cancel and you will get mole. So the volume is already in dm cube, so I don't need to convert it to dm cube again. So that's 11.25 mole. Now they want iron 2 plus and they want the mass and mole. Mole of iron 2 plus is equal to mass of iron 2 plus over the AR of iron 2 plus. If you think about the AR of iron 2 plus, it's going to be very similar to the AR of iron because only lost 2 electrons. When you're only losing electrons are so much lighter, to about 2,000 times lighter than protons and neutrons. Losing 2 electrons is not going to have a big impact on the relative atomic mass, which is to do with the average of the masses of the mass numbers, right? Which consists of the nucleon number, the number of particles in the nucleus, the protons and the neutrons, the heavy one, but not the electrons. Therefore, not much change in the mass at all. So we could just go straight to the periodic table. So 11.25 will give us the mass of Fe2 plus divided by the AR of Fe2 plus, which is the same as the AR of iron, assuming that they are going to be very light, the electrons that is. So divided by 56, there's the AR of iron. So the mass of Fe2 plus is going to be the mole multiplied by the molar mass. And I get 630. The answer will be in gram because of the unit preservation in this formula. So 630 gram is going to be the final answer there. Okay, so 6 part C, a sample of that much potassium. So this is potassium. And they say it's added to water. And then when the reaction was finished, you add some hydrochloric acid to it. First of all, what is the mole of hydroxide ions formed? Hydroxide ion is alkaline or basic. Alright, and what is the reaction? This is a metal plus water, one of the 5 general equations that you have got to know. Potassium plus water will give you metal hydroxide, so K plus OH minus, and it will also give you hydrogen gas. So to balance it, it's just half H2 as a gas. If you want, you can have 2, 2, 2, and 1, but it's the exact same thing for the purpose of balancing equation. Now, the mole of the hydroxide ion form comes from the KOH. So, the mole of OH minus is equal to the mole of the KOH. The mole of the KOH is equal to the mole of the K. Okay, I hope you can see that. So, the mole of the OH minus, the OH minus come from KOH. So 1 KOH give you 1 OH minus. 1 K give you 1 KOH, which give you 1 OH minus. So therefore, the mole of OH minus over the mole of K is equal to 1 over 1. 1 OH minus come from 1 KOH. 1 KOH come from 1 K. in terms of balancing equation there is. What is the mole of the hydroxide ions? Well, they just want the mole, so I don't need anything. I can just say the mole of hydroxide ions is equal to the mole of K. How much potassium did I use? I used 0.195. That is mass divided by mR. Well, in this case it's potassium, so potassium is going to be AR. So if you have a look in periodic table, the relative atomic mass of that, this is in gram per mole, mass over AR, because it's an element. So I get an exact answer of 5 times 10 to the minus 3, and then the unit is going to be mole. I look at the data given. This is 3 sig fig, this is 3 sig fig, this is 3 sig fig, and 3 sig fig. My data is not a 3 sig fig. It's important to be appropriate in terms of my number of significant figure, even when my calculator does not show me. It's a decision making that you will get better over time, hopefully, realizing from your data what kind of significant figure, what kind of accuracy does your data present you. On to the next part of the questions. So now you want the mole of hydrogen ions in the 100 cm cube of that concentration of HCl. So the HCl will give you H plus and Cl minus. Well, the H plus comes from HCl dissociating in water. So therefore, you want the mole of the H plus hydrogen ion, not hydrogen atom, not hydrogen meaning hydrogen molecule, but hydrogen ions, is going to be equal to the mole of the HCl, because 1 mole of these give you 1 mole of these. I could have done mole of H plus over mole of HCl is 1 over 1, which will give me this relationship just like that previously. So the mole of HCl is going to be concentration of HCl times the volume, which has to be converted to dm cubed because this is mole per dm cubed. So 0.100 mole per dm cubed multiplied by 100 over 1000, or I can do 100 times 10 to the minus 3, where I convert cm cubed to dm cubed. So that's just 1, and there's just 1 mole, but I should express my answer to 3 significant figure. Now give an ionic equation to represent neutralization reaction. So even though it's between hydrochloric acid, which is HCl, as well as potassium hydroxide, which is KOH, but they are specifically asking ionic. We did ionic equations many lessons ago, and you should know that neutralization reaction is between an acid, aqueous, plus OH minus, aqueous, giving you H2O liquid, because this is your acid, this is your alkali or your base, this is your water. Your salt don't appear because your salt is going to be soluble, and that came under solubility of salts, which I cover briefly, and I also ask you to look in the syllabus, in the latter part of the syllabus, under acid bases, preparation of salts, where we did relate the solubility of salt when we had to write ionic equations as part of your practice examples in those previous lecture tutorials many lectures ago. On to the last question. So this is question 7. Antacid tablets neutralize acids, and then blah blah blah. Antacid tablet contains calcium carbonate. You're gonna know your formula, Ca2 plus CO3 2 minus. The way you combine them is going to be CaCO3. So write an equation between calcium carbonate and hydrochloric acid. When they say equation, they don't mean word equation, but in your head you are thinking about word equation, because there is your most general 5 general equations, one of which is metal carbonate plus acid will give you metal salt, so it's calcium chloride, Ca2 plus Cl minus, chloride because you use hydrochloric acid, and you get CO2 and you get water. You have 2 Cl there, so I should balance it with 2 HCl. Now I have 2 hydrogen and 2 hydrogen there. CO3, one of the oxygen goes to the water, and another 2 oxygen get remaining on the carbon dioxide. This equation is balanced now. Now what is the mole of HCl used? So the mole of HCl, the HCl is actually, I don't think there's any way you can do this question without giving further data. Let me just retrieve the data you will need for this particular work first. So So yeah, you do need a data that I didn't include in this part of the question because it's actually part C rather than the whole question. So I'm just going to provide a little bit of that data. So experiment 2, in experiment 2, you have volume of acid in cm cube, which is actually 50, and then you have concentration of acid, and is given in mole per dm cube, and is 2.0. So based on this information for experiment 2, the acid that we used was HCl. So we have volume, but it's in cm cube. We have concentration, but it's in mole per dm cube. So you got to convert the volume to dm cube. Either you do divide by 1000, or you could do 50 times 10 to the minus 3, which is what I've done in previous part of this tutorial, or even in the previous tutorials for work 5, I think. So that's times 2.0, and that's it. There's mole per dm cube times dm cube. Put that into your calculator. So 50 divided by 1000 times 2, that give me 0.1. And this was given to 2 sig fig, and 2 sig fig, I would have thought that what is appropriate would be 2 significant figure, where this 0 in front of the first non-zero number does not count as a significant figure. So there's 2 significant figure, and I should probably write down 2 sig fig so that they can understand my reasoning there. Now they want the mass of calcium carbonate that will react with this number of mole of HCl. From our balance equation, 1 mole of calcium carbonate reacts with 2 mole of HCl. So they want the mass of calcium carbonate. The fact that they want the mass of the CaCO3 reminds us that we probably have to work out the MR of CaCO3, and that's what I'm going to do here. So from the periodic table, you have 40 for calcium, 40 times 1, plus 12 times 1 because 1 carbon, and 16 times 3 because you have 3 oxygen. That's going to give you 100 gram per mole. And I'm going to set up my mole ratio based on this equation here. So the mole of calcium carbonate is to the mole of HCl. I know I'm writing down to the edges now, but I just want to show you with the help of the equation still visible on top of this page. You have 1 mole of CaCO3 reacting with 2 mole of HCl. Now I can, lift this up and just show you this particular value here. So this is equal to, if I just bring down a little bit, this is how I label it. It could be the other way around, then you get 2/1. Does not matter whatsoever, as long as you could do the math correctly. So don't worry too much about which way around it is, except that one of it is what you want to find, and the other one is what you know. We know the mole of the acid as we did calculate it in the previous part of the question. So there's 0.10 mole of HCl that actually reacted. And I know that to relate the mass as well as mole, I'll have mass over the MR. So the mass of the calcium carbonate is what I want. So I'll label it as such. Divided by the molar mass. Mass over MR is the mole. On top is the mole of CaCO3 that actually reacted. At the bottom is the mole of HCl that actually reacted. Is equal to the ratio from the balance equation. Is equal to this thing which I label so that I'll never forget whatever I did. Now make the calcium carbonate the subject. I guess I can show you stepwise. So divided by 100. If I move that up there, so it's half times 0.10. Now if I move up the 100 one more time, essentially what I have then is the 100 will be gone, and it's just multiplied by 100 like that. So overall I can just key that into my calculator. So 100 over 100 times 1/2 times 0.1, meaning 0.10, that give me 5. That unit will be in gram because mass over MR, the mass is in gram, whereas this is a calculation based on data that was given to us in 2 sig fig. Hence I did 2 sig fig there. I should be appropriate and give my final answer to 2 sig fig. When the question didn't tell me to, I gotta think about what I had done as well as the data given in the question. It's not always 3 sig fig. This thing is just whatever is appropriate based on the data. They did not put down the unit here. If you just put down 5 or 5.0, you will not get any mark because this thing have a unit, because these masses have a unit. If they don't give you the unit, you have to write down the unit, which is why make it a habit to have a unit in your working, and therefore you remember it to put it in your final answer if they don't give you that. Alright, That's it for this lecture tutorial, not lecture tutorial. That's it for this tutorial on work 6 on mole calculations, further mole calculations, I guess, involving solutions. And don't forget to click the button on the bottom right to subscribe to the channel, and also follow the channel on the various social media platform at ptet.chemistry, ptet.chemistry, on Instagram, Facebook, and Twitter to get connected. Thank you for watching, and I'll see you in the next tutorial video.